Okay, and here we go. Let's get started for today. What we're going to talk about today is going to be very similar. It's going to be picking up what we talked about on Friday, and it's going to be about Newton's laws of motion. Before I get started, though, give me a thumbs up if you can hear this, so I know that we're all doing fine and there's no technical problems. Okay, seeing some thumbs up, seeing some fireworks and some hearts. Excellent, excellent. Um, so we talked about Newton's laws of motion already on Friday, and in particular we introduced Newton's first law. Today we're going to get to the point where we also talk about Newton's second law, and so that will be the topic for today. As a reminder, Newton's first law states that, and I'm going to write this down here. So Newton's first law. So I'm going to write this down here because I guess last time I didn't have the definition quite the way I wanted it and the way the textbook has it. So Newton's first law says that a body at rest remains at rest, or it remains, if it is in motion, it remains at constant motion unless acted upon by a force. So if we're at rest, we remain at rest. If we're in constant motion, we remain in constant motion, constant velocity. And the only thing that can change this is a force. And I'm actually going to modify this, and I'm just going to turn this into a net external force. So that the force has to be a net force. Could be a sum of forces, and it has to be an external force. So we're ignoring forces in we're ignoring internal forces. So we looked at that for this this case where a hockey stick hits a puck, and there's a couple of situations we can look at, and we actually started introducing free body diagrams. So I'm going to turn this into a little bit of an exercise on free body diagrams as well. So there's three situations we can look at here. We can look at what happens before the hockey stick hits the puck. We can look at the time when the stick is making contact with the puck, and we can look at it after the stick does not have contact with the puck anymore and the puck is sliding over the ice. So at first, so the puck, when it is at rest, we have the ice with the puck on top of the ice. And there's a couple of forces that apply here. So I'm going to draw the free body diagram here separately. So as you remember, we draw a free body diagram by having the body represented by a point and having all of the forces applied onto the point. So we have the weight of the puck. There's going to be a normal force from the ice onto the puck. So think of it as the ice pushing up against the puck. And since the puck is at rest, is not moving, since the normal force and the weight are going to be in our net force, they're going to sum up to 0. The puck remains at rest. As long as these are the only forces that apply, so the weight, we're often going to draw this just inside the picture of the situation as well, but think about this as the free body diagram is the diagram that doesn't have any of the other aspects drawn onto it. So the puck will remain at rest as long as the normal force and the weight are the only forces that apply here. So that's one situation. So clearly we're in the first part of Newton's first law here. Then while the puck is hit by the stick, the situation changes. So now we have our hockey puck here. There's still the weight that applies. There's still a normal force, but there's now also a force F due to the stick. So our free body diagram will look like this. We have a normal force in that direction, the weight in that direction, and the force F in that direction. Again, free body diagram is separate from the actual drawing, even though I've also drawn the free body diagram on top of this, the physical, the picture, the diagram of the situation here. So the net force now, F net, is N plus W plus our new force F. This net force is now non-zero. It's non-zero due to the presence of this additional force from the stick. And because it's non-zero, that allows our puck to not remain at rest or in constant motion, because it is actually acted upon by a net external force. So in this case, there's a net external force. So the puck can change from rest to being in motion. Okay. So yeah, one question in the chat there, when you're drawing a free body diagram, yes, we always draw the forces as coming from the point. A free body diagram, so don't do this, I'm going to draw it in red. Don't do this. N, W, and F. This is not the way to draw a free body diagram. It would just lead to confusion, because if you're just looking at this, you have to change the position of this vector to know where the net force is. It's much easier to see in this free body diagram that there's going to be a net force ultimately in the direction to the right. So always have your free body diagrams, the forces in your free body diagram start from the point and point in the direction in which the force acts. So the puck was at rest first. They got hit by a stick that allowed it to change from rest to being in motion. And now the puck is in motion. The puck is in motion, and no more contact with the stick. So now we have the situation where we have the ice, we have the puck, there's a normal force, there's the weight, and so the free body diagram again looks like this, and the weight. So I'm gonna put this in a box again to separate it from the actual from the drawing of the situation here. The net force now is equal to 0. It's still N plus W. All of those normal forces and the weight, of course, didn't change. So if the net force is 0, then the puck remains in constant motion. So it will start at v equals 0. It will change its velocity. V will increase in this case, and then v will remain constant in the case of as soon as the stick does not touch the puck anymore. Now there's of course an assumption here, and the assumption is that there's no friction. That's why we're talking about a puck on ice and not talking about a puck on the street, street hockey, I guess. And the reason is, of course, that allows us to a very good approximation to ignore friction. So ice, anytime when we're talking about ice or about air tables, this allows us to ignore friction. And of course, we know that there must be some friction, because even a puck on ice will ultimately not keep its velocity at a constant value forever. And I don't mean that it hits the sides of the hockey rink, but it will ultimately slow down, and there will be some friction, and that is, in some sense, a force. This force of friction, not just in some sense, it's a real force, and so we have our normal force or weight, and so there will be a little bit of friction here. I'm going to draw a little force, little f, such that the net force now is little f, which is non-zero, and that will allow, or not just allow, but will forces, or will cause, let's say cause, will cause the puck to slow down. And in other words, change its velocity until, of course, it's at rest. And what happens when it's at rest? Well, when it's at rest, there's no friction, or there's no force of friction, and so we're back at this situation. And so when it's at rest, it can remain at rest without violating any Newton's first law. So one thing you'll see sometimes is that in these diagrams, we'll also draw the velocity to indicate that in this case the puck is going in this direction, the friction is pointing in the opposite direction. Friction is always going to be pointing in the opposite direction as the velocity, because friction tries to stop the velocity, stop the direction of the velocity, not help the direction of the velocity. However, keep in mind that these velocities, this is not a vector in the free body diagram. So make sure that you don't draw, again, I'll put it in red, don't draw something like the normal force, the weight, and then the velocity, and then the friction. This doesn't make sense. We can only have forces in a free body diagram. Only forces in a free body diagram. No velocities. Okay. Good. So let's go back to the slides here for a second. So we've analyzed the situation both before, during, and after the time when the stick hits the puck, and so we can use Newton's first law to describe the motion. Now, of course, we can look at other situations. So, for example, in this case here, we have a car that's parked. We have a car that's parked. There's no net force on this. So if the velocity is 0, the net force is 0, the car is parked, everything is fine, and it satisfies Newton's first law. In this case, we have a car going at a constant velocity of 50 kilometers per hour, going in this direction. What's the net force on this car when it's going at 50 kilometers per hour? So indeed, the net force on this car is equal to 0. The reason why the net force is equal to 0 is because it's moving at constant velocity. I don't have to know anything about the shape of the car, the friction with the tires, the air resistance. I know that the fact that the car is moving at a constant velocity, Newton's first law says that means it will have to have the net force will have to be equal to 0. Okay. So, of course, we're going to have to make the non-zero-ness of net force a little bit more precise now, right? So if we have now, in this case, you have two students here pushing a car, so we have two forces, F1 and F2, that are pushing the car forward. There's a force little f, that's our friction, that's going in the opposite direction. And then there's a normal force and a weight that is acting on this car. So these are the external forces on the car, and so in the free body diagram we draw these forces in the direction in which they're applying. Now, the same thing can be true for a tow truck. Now there's only one force, the force from the tow truck that is moving to the right. There's the force of friction that's moving to the left, or that's pointing to the left, and then the weight and the normal force. Now, how does this situation differ from this? And in particular, how does it allow the car to accelerate more quickly here than in this first situation when the two students are pushing it? Well, that's of course going to be the topic of Newton's second law. Newton's second law, which allows us to treat those situations where we have a net force, a net external force, and turn it into a statement on acceleration and a statement on the change of the velocity that we observe, that we predict. So, okay, let's not go to that slide yet. So let's look into those cases when there is a net force that is non-zero. So that's going to be Newton's second law, which in words is, what happens when the net force is non-zero, the net external force. So there's a net external force on an object, on a body of mass m. So that's what Newton's second law is going to explain. Of course, before we go into that, we probably want to talk a little bit about what mass is. So the reason is that there's clearly a difference between masses. If you push against a basketball with a certain force, you can make that basketball move pretty quickly. But if you push against a car, which has a different mass, which weighs a little more, and we're going to talk about weight and what that means when I say that. So when you push against a car with a larger mass, you cannot make it go at the same speed as you can make a basketball go, even though you're applying the same force. So mass is going to have to play a role. So let's talk about mass and about inertia. So mass is going to be the tendency, or the quantity, and in particular inertial mass. Inertial mass is the let's call it the amount with which an object resists changes in motion. So an object with a large mass will resist changes in its motion more than an object with a small mass. Heavier objects require, or will require, a larger force to change their velocity, so they will have a larger inertial mass. So this term inertia, which is used here in inertial mass, we should also define inertia is the tendency of an object, the tendency of an object to maintain its velocity in both direction and magnitude, of course. It's a vector quantity. So one situation where you probably well, we'll come back to an example of inertia. So if we talk about inertia, that gives us inertial mass, which is the amount of the amount to which an object resists changes in its motion. The other thing we're going to talk about is inertial reference frames. And I already talked about that a little bit. So those are reference frames. Those are those reference frames that we talked about. Those are the only reference frames that we're going to talk about in this course that are related by a constant velocity. So those are reference frames that move at a constant velocity. Again, direction and magnitude has to be constant. So in other words, a reference frame, an inertial reference frame, is a reference frame, or actually related to Newton's first law. An inertial reference frame is, or for every object that satisfies Newton's first law, I can find an inertial reference frame in which that object is at rest. So for every object where Newton's first law applies, Newton's law, not just Newton's law, Newton's first law, well, let's make it we can find an inertial reference frame where that object is at rest. So if we go back, for example, to the car moving at a constant velocity of 50 kilometers per hour towards the right here, we can find an inertial reference frame where that car is at rest. And of course, then the situation in that reference frame becomes just the situation in panel A. So if we have an inertial reference frame that moves at a constant velocity of 50 kilometers per hour, then that car will be at rest in that inertial reference frame. Okay. So then the other thing we can talk about, let's skip this here. We can talk about equilibrium, which is a situation when there's no net force on an object. So of course then an object that's at rest will remain at rest. An object that's moving will remain moving, but there will be no acceleration. And anyway, but we'll come back to equilibrium later. So let's look at, now that we've introduced mass, and we know that if the net force is not equal to 0, there has to be an effect on the object that depends on the mass to some extent. So we're going to formulate this now into Newton's second law, which of course, as some of you already know, says that the acceleration due to a net force that's non-zero is that net force divided by the mass of the object. So in a sense, if the net force is not equal to 0, then A is also going to be non-zero. There will be an acceleration. And yes, you're probably also familiar with the other way to write this. That's the net force is equal to m times A, F equals ma. But really, causally, these are the things that are inputs, and this is the thing, the acceleration is the thing that's an output. So in some sense, this way of writing it is more physical, even though this way of writing it as F equals ma avoids having to have a fraction in there. So that might be easier to typeset in a textbook. But it makes sense to think of the F equals ma as A equals F over m from a physics point of view. So in the case of the problems that we're going to try to treat now, we're going to have to identify the net force. We're of course going to identify the mass of the problem, mass of the object, and that will allow us to calculate the acceleration. One thing I will note here for completeness is that m must be constant for this expression. Now you might be wondering, okay, well, what are some situations where f would not be constant? I mean, how could you have an object that doesn't have constant mass? Well, one typical example is a rocket that is launched. There's typically so much fuel in a rocket that its mass changes substantially over the course of its trajectory, and when it's moving, when it's changing its trajectory, that will have to change the acceleration, not just due to the net force, but also because the mass changes. So let's go to, for example, these problems. So now we're going to have to take or net force in this case, which is non-zero, and turn it into an acceleration. Same thing here with the tow truck. We're going to have to turn that net force into an acceleration. Of course, that requires that we know the mass of the car, and of course know something more about the forces here. One thing that we have to be careful about is, of course, identifying the right forces that we want to add up in the case in order to get to our net force. So I'm putting here a picture that was in this textbook until very recently. I think probably just a year or 2 years ago. And I'm putting this here not to show you incorrect information, but to show you that this isn't a trivial thing necessarily to identify the right forces. So in the case of a car that's accelerating by 10 meters per second squared, the picture in the car was, a picture in the textbook was that these are the forces working on this car. There's the force of the engine moving forward or pushing the car forward, and there's the force of friction that is drawn here as if it applies at the wheels, and that is pushing the car back. Now, is this correct? No, this is not. I mean, the force of the engine might be a nice way to think about it, but this force, there's no external engine that is pushing against this car. So this force of the engine is not an external force. That doesn't apply. That doesn't play any role in the sum of our forces to get to our net force. The updated picture now that's currently in the textbook, and that's the correct picture, is this one. So what's actually pushing the car back is the drag, the air drag. That's the resistance that the car has to overcome. And you'll notice that the friction is actually the thing that is propelling the car forward. It's the internal forces, which we don't want to add up in our net force total. It's the internal forces that cause the tires to rotate, and the tires rotate in such a way that the friction with the ground is pushing the car forward. So it's this friction that's applying, and it is pushing the car forward, as opposed to in this older drawing, the friction pushing the car back. Friction is pushing the car back if there's an external engine that pushes the entire car and it's just sliding over the ground. Then this would be the correct interpretation of the forces. But when a car is rolling and is driving on its own and there's no external engine, then the force that is keeping the car back is the drag from the air, and the force that is propelling the car forward is the friction with the ground. So I'm just putting this here because it's easy to make mistakes in the interpretation of which forces are important. And of course, depending on which assumption you make, you might even end up with the friction pointing in the completely opposite direction. And I'm pointing out here that this is not something that everyone gets right, even people who are writing textbooks that are used by hundreds and thousands of people around the world. Okay. So that's so where are we at here? Okay, so now that we have our forces, and in this case there will be, of course, a net force. If the car is accelerating, there's going to be a net force in the forward direction, which means that the force of friction will be larger than the force of the drag, and so the net force will be in the positive direction. So I see a question, would the friction still apply on the rear wheels? Well, yes, indeed. Of course, it depends whether it's front wheel drive or rear wheel drive, but it will apply on the wheels that are actually going to be the ones that propel the car forward. So of course, in this case, we can treat this as a one-dimensional problem. The net force will be along the horizontal direction because the acceleration is along the horizontal direction. But obviously, we'll also want to treat this as a vector law. So we'll be able to split this in an x component, which is going to be the x component of the net force over the mass, a y component, which is going to be the y component of the net force over the mass. And of course, everything will just translate that way. And I can add a z component here for those problems when we're in 3 dimensions. And then, of course, the acceleration will be given by the z component. So in the case of the z component. So if we look at, for example, a problem like this, where we're given the forces along different directions. So F3 is going into the negative x direction at 5 newtons, and F4 is going in the positive y direction at 2 newtons. F2 is going into the negative y direction, and F1 is even at an angle here. To calculate the net force, we're going to have to calculate the components of F1 in the x and the y direction, and calculate the components of the net force in the x and the y direction to calculate then the acceleration in the x and the y direction separately. And then, of course, we'll end up with an acceleration vector. Okay. So this way of writing the acceleration, there's another this way of writing Newton's second law. There's actually another way we can write Newton's law, and that's by introducing the mass and the acceleration and combining them, or the mass and the velocity actually, and combining them as a single property of the object. So if we have so let's call this an equivalent formulation. But in this case, but with the mass on the side of the object's properties. So we're going to put it on the side of the object's properties, which is the acceleration. So what we'll introduce is the momentum, which is again a vector quantity, which is m times v. So mass of the object times the velocity of the object will be the momentum, and then or expression here, which was A equals F net over m, now becomes that the change in momentum over time is equal to the net force. So dp dt is equal to d dt of mv, and so for constant mass, m constant, this becomes m times a, and so of course if F is equals ma, then F will be equal to dp dt as well. So our momentum, the time derivative of our momentum, is the net force, or the net force that's applied externally will cause our momentum to change. And so the benefit of this, of course, is that this law will be valid even when m is not constant. The thing that requires m to be constant is the part that turns it into F equals ma, but this is true even when m is a function of time. Okay, so just to check, so let's ask a couple of questions here. So question 1, in projectile motion, let's imagine you have an object and you throw it straight up with an initial velocity. So what will happen is, as a function of time, the height will change like this, right? With our parabolic trajectory. So there will be a highest point here. And at that highest point, v is equal to 0, right? So the moment, at that point, that object is momentarily at rest. Is the net force equal to 0 on that object at that time? So take a minute to think about that. So is the net force on an object in projectile motion equal to 0 at the time when it has reached its highest point and when it is momentarily at rest? So I see a couple of good answers there. No, the net force is not equal to 0. Why? Well, we know it cannot be equal to 0 because the object is accelerating. The acceleration is minus g in the y direction, right? That's non-zero. So that makes sure there must be some external force. There must be an external force which is causing this acceleration, which causes the velocity to change. And that external force is, of course, the attraction due to gravity. So if we were to draw the object at that time and draw a free body diagram, the only force that is operating on that, or that is exerted on that object at that time, is W, is the weight. That's actually the exact same force that at any other point in the trajectory is exerted on this object. Because it goes through this maximum and v is momentarily 0, that doesn't mean that the net force is 0. It means that the acceleration, the only thing that means that the net force is 0 would be if the acceleration is 0. And the acceleration is never 0 along anywhere along this this parabolic trajectory. So the next question is one where I'm going to have you talk in your your little groups that you're sitting in now, because each of you are in like a group of 6, and it might be different from your regular groups, but that's fine. So let's say you're driving along the highway, or let's not pick the highway. You're driving along a busy street in Winnipeg, and you are getting close to an intersection. You're going on you're on your way to the university, and you've got your bag on the passenger seat. Of course, your bag isn't buckled in with a seatbelt, and you get to an intersection and you have to brake suddenly for a red light. So what happens is, as you know, your bag is going to slide forward and fall on the in front of the passenger seat, and you yourself, you're going to still sit in the car. So explain or discuss with the people sitting around you, what are the forces that are applied on the bag and on the car when you're stopping, and why does the bag slide forward, and what is preventing you from sliding forward, and how does this relate to inertia? How does this relate to the different reference frames, and how does it relate to Newton's second law? So what are the forces that apply on the bag, and draw a free body diagram. Let's start with that. So I'll give you a minute to talk about that here, and that will be then the end of class. So talk to your neighbors about this. What are the forces on the bag when you're braking?